I'd like to welcome you to the 21st Emiliani Lecture. We have the list of previous lecturers up here, and this year we are happy to have Hai Cheng as our Emiliani Lecturer. Okay, so this lecture is named after Cesare Emiliani, who is considered to be the father of paleoceanography. He was a foraminiferal micropaleontologist who completed his second PhD in Chicago with Uri and established the science of isotope paleontology. And then he moved to Miami, where he had use of an oceanographic ship and the Caribbean. He was instrumental in developing or getting deep sea drilling started and establishing that ice ages were cyclic phenomena over the last 500,000 years. And so his paper in 1955 was seminal for that. But he ran into two technical problems. I'm going to bring them up because it relates to our speaker today. One of those problems was that he underestimated the amount of depleted oxygen isotopes in continental ice, and that led to Nick Shackleton developing the method of using bank-thick forams to try and assess that. And he also underestimated his sedimentation rate. There was development of the uranium thorium dating technique on coral reefs that was beginning to confound his results. So a tradition of the Emiliani Lecture is you talk about how you met Emiliani and what his influence was on your career. So it turns out I did meet him. There was a 2-day discussion on the interpretation of speleothems back in 1972. My father did most of the talking because I was about 6 months old at the time, but there is a connection. But that leads nicely into this lecture, because speleothems languished for about 20 years after that until development of uranium series dating in caves improved the dating of cave techniques, and people really began to understand the systematics of speleothems. In the late 90s, a very special speleothem came to Minnesota, and through the Coma Fellows and with work that Hai Cheng did with Larry Edwards, the Hulu Cave speleothem was developed, and we're still seeing its influence on our dating and on our understanding of paleoclimate records today. So, our Emiliani Lecture today is special for leading developments in uranium series dating, addressing some of the fundamental questions of paleoceanography and global climate change. He's been a leader in improving the dating techniques, as well as producing some amazing Asian monsoon records, including the iconic Hulu Cave record. That has improved our paleoclimate data from around the world. Now, I know some people are really into numbers, and so I've got some numbers up here, number of publications, where they were published, H-index. Everyone loves the H-index. And I think you'll agree that Hai Cheng is highly qualified to be our Cesare Emiliani Lecturer. So with that, I would like to welcome to the stage and stop talking and let him tell you about his science.
Thank you for your introduction. This is a great honor for me to give this talk. Okay. So probably I might not be able to use this anyway. So my topic is isotopes in speleothems and global climate change. Mainly, I'm going to address some aspect of orbital theory of climate. If I have time, I'm going to talk a little bit about the 100,000 problem. This is a classic problem in this field. And the triple oxygen isotopes. Okay, I do not need this. Okay, oxygen has 3 isotopes, 18O, 16O, and 17O as well. 18O, 16O ratio is commonly used with a delta notation we call data weighting. This is the definition. In our field, this picture has three very great scientists. Emiliani applied delta weighting analysis to thoriums and demonstrated the cycle of ice ages. Urey discovered a method for measuring paleo temperature by delta weighting analysis of marine carbonate, and Wassenberg developed uranium theory's TIMS method in his lab in 1980s. In 1955, Emiliani published his long record, temperature record, based on measurement for delta weighting of thoriums. His pioneer work provided some of the world's first continuous record of interglacial cycles. These records laid the cornerstone of the Milankovitch orbital theory of climate and forever changed our view on the Earth's climate system. Following his pioneer work, there are a bunch of milestone works toward more and more robust marine delta weighting reconstruction. Notably, however, all the chronologies are still essentially based on the orbital tuning strategy with one of the basic assumptions, phase lag of 5,000 years to some insolation at a precession band. At precession band, that means ice sheet response insolation forcing with a 5,000 years lag. This lag is originally in Milankovitch hypothesis as well as in Emiliani's delta weighting record. But the lag has not been really well tested by absolutely dated climate proxy record. This is partially because the thorium itself can get temperature signal, but no matter what's the precision or accuracy, it could. For example, this equation, this is the early version equation used by Emiliani. However, direct uranium-thorium dating of thoriums is not presently possible because thorium has low uranium concentration, possible thorium-230 contamination, and diagenic addition and exchange of uranium, which is, of course is a sort of a open system behavior. So besides marine delta weighting record, do we have a long and continual climate record to use? The answer is yes, of course. For example, ice core record is continuous and long enough now, but the chronology of long ice core records are based on orbital tuning, essentially. There are a bunch of long and continuous beautiful lake records. However, the chronology of this long lake sediment record are also based on orbital tuning strategy. Earth record is continuous and long enough, but chronology, again, based on orbital tuning. So basically, chronologies of long marine, lake, Earth, and ice core records are all based essentially on their orbital tuning strategy. Therefore, everything is correlated to everything, which is good. Probably there are other sides which make it difficult to resolve the phase difference, especially the precession phase differences. Therefore, do we really have a record with independent chronology or absolutely dated chronology? The answer is also yes. Cave delta weighting records are suitable for independent and absolute uranium thorium or uranium lead recently dating, and now long enough to test the orbital phase difference between climate records. Regarding spatial coverage, Emiliani said a long time ago he himself was instrumental in initiating the deep sea drilling project, a project that finally revealed how the Earth works. After that, then in the past, the ODP and the IODP project indeed have covered the ocean globally. Then ice core record covered the north and the south polar regions, Greenland and Antarctica. In the past 20 years, cave data 018 records have covered most of the land region, become an important complement to marine and ice core record. Therefore, now we do have a global view. People in our field familiar with ice core delta weighting record, most of them, I mean, paleoceanography or paleoclimatology field. For example, Greenland ice core. This is probably because the snow has a lot of climate signal in the snow. For example, delta weighting of snow. So the snow accumulated in the polar region turns to ice gradually. You drill an ice core and measure the ice delta weighting, you get an ice core delta weighting record. For example, this is an Ingrid record. In low and the middle latitude, however, we do not have snow accumulation. However, we do have a lot of rainfall. Rainfall has similar climate signals, such as delta weighting. Most of the rainfall evaporate back to air or run off back to ocean. However, there are a tiny portion of those rainfall water get into cave system involving the formation of a speleism. Essentially, this process propagate delta weighting of rainfall to the groundwater or dripping water, and eventually fix this delta weighting signal into the speleism. If you get a sample of speleism and cut it and polish it and measure carbonate, this delta weighting, you get a cave delta weighting record, such as a Hulu record, as mentioned before. Okay, both ice core delta weighting record and the cave delta weighting record are equally important. For example, both you use both records, you could get the Asian monsoon variations and Greenland temperature record and correlate them convincingly together. Speleism, in general, is a calcite or aragonite. These minerals contain a lot of isotope systematics that are very useful for paleoclimate research. However, here I only can mention like uranium-238 decay chain for uranium thorium dating and oxygen isotope for the climate proxy. In the early stage, uranium series dating is always powerful. For example, Wally and his colleague dated the coral reef in 1968, and they immediately found a precession cycle of a sea level change, like 5E, 5C, 5A, provided one of the convincing evidences that supported the Milankovitch hypothesis. Okay, in our field, this first uranium-thorium dated cave delta weighting, I believe, came from southern France in 1970, which characterized continental climate variations from 130 to about 90,000 years ago. In 1980s, Tim's uranium-thorium dating method replaced the early alpha counting method, and the Washenberg, Chen, and Larry Ellis did substantial contributions. Later, Washenberg commended this development, said that sometimes science advances because of a new shovel, this method basically, and the urge to dig a hole somewhere. Recently, multi-collector ICP-MS, this technique further improved the uranium series dating. Now we do have a new tool and the urge to dig a hole somewhere. What we could do, first thing I thought is test the phases of climate records at precession band. For example, to test the ice volume phase at a typical ice proximal region, such as in this country, like West Virginia. Why precession? Precession actually contributes much more to insolation changes from low latitude to middle latitude, even to high latitude. At precession band, there are two types of climate response. We call it later and early response relative to summer insolation. Okay, this is a phase wheel to show precession phase lag to June or summer insolation. According to Ingrid, northern hemisphere climate change lags summer insolation by about 5,000 years. They also noted there are some climate change of like show like early response like southern hemisphere SST. Later, Rudiment emphasized that in ice-proximate regions, climate change lags summer insolation by 5,000 years, similar to ice sheet. Therefore, we think this cave record is going to be very important because we call it the BCC, okay, from West Virginia, because it simply very close to the ice sheet, but not underneath the ice sheet. Otherwise, you won't have a speleism growth. Okay, so what to test in North America? First, of course, the late response, 5,000 years lag to summer insolation, or northern summer insolation forces a lagged ice sheet response and the transfer to proximal regions. This is one of the key aspects of actually the Milankovitch theory of climate. Okay, in North American cave record, there is a very famous early stage work from Davis Hall, and it showed that termination, ice age termination too, sort of lead insolation rise by 10,000 years, which challenge Milankovitch theory. Recently, another group, okay, went back to the same cave and get a bunch of new samples. What they found is that different samples from different depths have different timing of termination too. They believe the shallow sample, like a 2.1 meter above the current cave level, is most reliable. Okay, therefore it lacked the insulation, but in terms of precession phase is still unclear. In this year, we established, we pushed the BCC cave further back into like for 350,000 years. Therefore, we have long enough record to test the phase of a precession band. What we found is that at precession band, it in phase with September insolation, therefore consistent with ice volume change. Underlying mechanism was considered as ice volume forcing, and together with sea ice forcing. This diagram, the left one, show the precession phase relative to BCC, the cave delta weighting record, on the precession scale. So you can see that the precession phase of North American climate change, including Davis Hall, the new data, and Gulf of Mexico SST, ice volume, Nevada caves, seems to have same phase relationship with 5,000 years lag to the summer insolation. Then what to test the region remote to the ice sheet? We want to search for the early response, for example, the low latitude monsoon variation and other climate variation at the precession band. If yes, I think this was not included in the sensu stricto Milankovitch theory. So in monsoon regime, a classical wisdom from John Kutzbach is this: the monsoon rainfall are in phase with summer or July insolation at precession band. This is mainly from a model simulation result. And in real world, you also can see this scenario directly For example, the regular sapropel deposits in the Mediterranean, like 8 to 9 million years ago, demonstrated that the eccentricity modulated orbital precession cycle clearly, which indicates Northern Africa summer monsoon variation before the full-scale Northern Hemisphere ice sheet. After the full-scale Northern Hemisphere ice sheet, variations of North Africa lake levels also follow precession cycles. For example, African lake level were much higher at 9,000 years ago. And the sapropel record also show that the Northern Africa summer monsoon follow some insolation. In China, an important observation recently was the Asian monsoon delta weighting tracks the July insolation, which provide a robust early response example. Okay, this diagram shows the inter-hemisphere contrasting of seasonal precipitation amount and the seasonal precipitation delta weighting. The record from the Sandball Cave at the top green curve is from China, Northern Hemisphere. The bottom curve is the Tapachi Cave record from Brazil in Southern Hemisphere. They follow Northern Hemisphere insolation and the Southern Hemisphere insolation respectively, therefore display anti-phased precipitation delta weighting relationship on optical scale. Overall, we do have a monsoon hypothesis that global monsoon is primarily driven by summer insolation on orbital scale with inter-hemisphere anti-phase relationship. This is the simplest hypothesis, which I think tends to be right. If you believe Ackermann's razor, which is all things being equal, the simplest solution tends to be the best one. In addition, we also found that the Asian westerly climate is also in phase with July insolation. For example, the cave record from a Sarak cave, Israel, or cave record from a town record in Uzbekistan, Central Asia. We knew that Asian monsoon delta weighting record has a great or very close relationship with the atmospheric methane. On longer time scale or orbital scale, we also can confirm that the methane variation is in phase with the July insolation at precession band as an early response greenhouse gas. They're very close to Asian monsoon. 10 years ago, Jeff Seminghaus found that the Doha effect or delta weighting of O2 is primarily controlled or governed by the strength of the Asian and the North African monsoon. On the long time scale, on orbital scale, we also confirm that delta weighting of atmospheric O2 variation is in phase with Asian monsoon at precession band. We also knew that atmospheric CO2 has close relationship with ice volume. So we also found on the orbital scale, the CO2 variation is in phase with ice volume at a precession band as a late response greenhouse gas. So overall, we see late response as predicted, like ice volume, like North American climate, and atmospheric CO2. We also see a bunch of early response like monsoons, Southern Hemisphere SST, I'm not quite sure, okay. Then Asian westerlies and atmospheric methane and the delta weighting of CO2. So the question here is really this: the early response are not really included in Milankovitch's theory of climate yet. So according to Andrew Berg, the arm of the orbital theory of paleoclimate is to study the relationship between insolation and the climate at a global scale. Orbital theory contains 4 aspects. Orbital elements, of course, solar radiation, climate model simulations, and geological observation data. Among the four aspects, it is foremost that the cave records have provided new observational evidence, global monsoon that's, follows antiphase the precession cycles between south and the north hemisphere, providing one of the new geological observations for a more comprehensive orbital theory of climate. In 1992, Ingrid wrote, because our focus is on the process of glaciation, we exclude the low latitude side, where previous work has shown that climate history is dominated by change in the monsoon circulation. In fact, this strategy may well exclude the consideration of low latitude processes that could be important. Here, we suggest including, not excluding, the low latitude processes that are important to me for reaching a more comprehensive orbital theory of climate. Here is a list of milestones in evolution of the orbital theories. Of note is cross hypothesis. Cross hypothesis is important because it predicts multiple antiphase ice age occurred on precession cycle in two hemispheres. His core idea was inter-hemisphere contrasting climate changes at the precession band. He emphasized the winter insulation forcing on inter-hemisphere ice age, which was wrong. But recently, cave record also showed the core idea, like some summer insulation forces, summer, not winter, on inter-hemisphere monsoons, not ice ages. So that's probably why 2006, Fleming commented that cross hypothesis started a Copernican revolution in climate dynamics, and while this Milankovitch served as the Newton of this field, our field, about a half century later. Okay, indeed, the core idea is consistent with the new cave data. In China, there's a long-standing question that is, while modern climate research has demonstrated clearly that the low-latitude process, such as ENSO, can play a critical role in driving global climate change, why only not high latitude is obviously important in paleoclimate research. Okay, here a new cave data show Asian monsoon leads the ice volume change by 3,000 years at precession band. So those two records from North American and the Asian monsoon. The dominant precession cycles really have like 3,000 years plus minus 1,000 years differences, with Asian monsoon lead the North American climate. This observation is significant because it demonstrates a more active role of low latitude climate in global climate change. Regarding insulation forcing, there is very important or interesting similarity between the two major insulation forcing. One is the summer insulation at 65 degrees north, which is considered as a driver of ice volume change. And another is the summer insulation of 30 degrees north minus 30 degrees south, considered as a monsoon driver. Okay, however, those two forces are virtually indistinguishable. They are just overlapped. So therefore, the phase relationship becomes critical for understanding the mechanisms. The leader of monsoon at precession band suggests the following loop. At precession band, the monsoon intensification might cause the rising of the water vapor and the methane in atmosphere, which may act as an additional force to ice sheet decay. Ice sheet decay may act as a positive, provide a positive feedback through CO2 and the temperature to further intensify the monsoon variation. Anyway, the loop is this directionality, not the opposite, therefore suggesting a more active role of low latitude climate. I want to mention one thing that's around the equatorial. The complicated pattern may be the last piece of the puzzle of the orbital theory. For me, I didn't see very clear evidence for 10 and 5,000 years cycle as predicted. And instead, we see some South American dipole on precession scale, but only in interglacial, not in a glacial time. We also see some very large excursion of the termination along from Colombia, 8 per mil or even large. And we see some kind of unusual long MIC11 from Borneo at Central. However, some clues are already there, I believe, and the full picture is emerging, although there is yet much to be done. Here is my first summary. New observation data over the past half century may be used to formulate a more comprehensive orbital theory of climate, which should at least incorporate precession-induced summer insolation forcing in driving the low latitude climate change and the interplay between low and high latitude climate. Okay, do I still have time? No, probably I can go through the second topic a little bit. It's probably what I have, huh? A little bit of time. Okay, I'm talking about a little bit about this 100,000 problem. The problem, as you probably knew better, is this. The orbital eccentricity contributes much less to insolation change than precession and obliquity. However, the most significant observed change over the past 800,000 years was the 100,000 years glacial interglacial cycle close to orbital eccentricity cycle. So there are a number of hypotheses there already trying to resolve this classical long-standing issue. Here is our approach. This is the Asian monsoon record we mentioned before. Then we knew that it follows summer insolation closely. If we remove the insolation or with long-term this kind of components, we get a residue. Well, I believe that the residue therefore characterize millennial scale climate variations. Here is delta D record from Antarctica. If you remove the long-term, mathematically long-term trend, then or the long-term trend actually is the identical to benthic delta weighting record. Therefore, you get another residue record. Therefore, we think this characterized millennial scale climate variations. Those two records that virtually are just the same. So this is not surprising because the tally connection between Asian monsoon and Antarctic temperature is significant. For example, you can see those two records can overlap during the last glacial period. Then it demonstrates a simplicity if you like a delta weighting, a cave record. You remove the insolation component, you're going to be equal to the Antarctic temperature, remove the delta weighting of benthic. So on the other hand, ice age terminations can be viewed as larger millennial events, and other millennial events can be viewed as small termination events. For example, as people call it, whatever, low latitude or amplitude version of termination or failed terminations or unfinished terminations. Anyway, ice age termination events and other millennial scale events are essentially similar except their amplitude. So now we think we have millennial scale climate variation records, those residue records, as I mentioned before, including terminations and other millennial scale events. if we do spectral analysis, and then we found that the millennial climate variations, including the ice age terminations, have more significant precession and obliquity periodicities than eccentricity. This, I think, may partially explain some aspect of 100,000 years problems. Here is the second summary. Our results suggest an impact of Northern Hemisphere summer insolation on millennial scale climate variations, including glacial terminations and other millennial scale events, which may partially explain the long-standing 100,000 years problem. If I have a few minutes? Oh, still?
You've got
Plenty time?
Yeah.
Oh, okay. Now, 18 minutes you're talking about?
Yeah.
That's too long now. I thought its total time is going to be 50 minutes. Sorry about that. So therefore, the third topic is about recently progress in triple oxygen isotope. So technically, there is a difficult because isobaric interference on the mass 45 if you want to measure CO2 directly. CO2, of course, is released from our carbonate samples directly by the acid. Therefore, we have to develop some method to convert CO2 to O2, then measure O2 in order to measure triple oxygen isotope of the carbonate. So there are two ways to do this conversion. We used the second way, which we think here the second way, we think that way is much better. So in terms of triple oxygen isotope systematics, I think we pretty much understand what's going on, but this is our understanding. It's not that complicated, but to be simplified, essentially, basically, we would like to measure carbonate, delta 17O axis. Then for this notation is a little bit funny, but because it's a conventional problem, therefore we can get the information of the rainfall delta 17O axis, which then we can use to get the relative humidity at the moisture source regions. So here is Earth's surface relative humidity and cave size. We already have some kind of a preliminary data from those cave sizes already. So, and also you can see some example of the data. For example, the cave data from Central Asia show that it looks like it follow winter insolation and winter precipitation now, okay, regime, okay. There also seems there are some correlations with local wetness or delta 7, C13. We also have a little bit marine data from West Pacific wormhole. It looks like the data follows local summer insolation and has a little bit of correlation with the summer monsoon variations as well. So overall, in Emiliani era, the 18:16 ratio or isotopes indeed had played a critical role in paleoceanography and paleoclimate research. In the future, I think the triple oxygen isotopes may be important to understand paleoclimate variations on the various time scales. Now we have, we are at the stage to have a bigger picture about the 17 axis in a global scale. So just like 1955 when Emiliani published his bigger first order, what's the glacial interglacial cycle might be looks like. So here is the third summary. I think in prospective triple oxygen isotope may provide new insights into global hydroclimate variations and underlying dynamics. Okay, thank you for your time.
So before I open up to questions, I would like to present Hai with his fancy certificate from AGU.
Well, thank you so much.
So questions?
Guess I left. Okay. 100K problem, as I mentioned, is because the insulation, it's tied to the initial Milankovitch theory. Milankovitch theory extend that summer insulation at like 65 degree is the main driver of the ice sheet change. Then the ice sheet change affect the global climate. Basically, the main idea is this. Therefore, the paleoceanography evidence show that in terms of periodicity, they match Milankovitch cycles like precession, obliquity, eccentricity. But as I said, the contribution to the insulation change is mainly from precession cycles and obliquity cycles, not eccentricity cycles. But the evidence from marine or this delta weighting is actually the largest amplitude is 100,000 years, about 100,000 years cycle, not as predicted as the insulation cycle, which is dominated by precession and obliquity. So this is the problem itself. Then it's still the problem until now. But I think if you just take the insulation, the ice age termination, and the other millennial variability. Ice termination is millennial variability, like several thousand years termination really fast. So therefore, if you do statistics or this analysis, you're gonna see the main periodicity is not precession. It's indeed, not eccentricity, is indeed precession and obliquity. That means the long-term or the ice age, this 100,000 years problem is more or less not an insulation cause. It's possibly it's just internal this the ice sheet dynamic decided contributed to the 100,000 years problem. This is our view on this issue. So. That's also a good question. I personally think we do have some kind of split record that further back to 1.5 million years now, but not published yet. But to our record, we still see the precession cycles dominant. But the marine record, you know that it's 40K as a word, right? The 40K, it's sort of like, I personally don't think the precession dominant, that this precession is still dominant, because the same reason, just the ice sheet or temperature boundary condition are slightly different. Therefore, the internal ice sheet dynamics is slightly different. Therefore, everything is consistent. Yeah. This also is a long-standing issue. For example, the marine record is not really match the land record. For example, cave record and Arabian Sea record, and there are some fundamental discrepancy there. For Indian monsoon, we do have long-term record, which really match Eastern Asian monsoon nicely, but there's a difference. There is a slightly larger component, or periodicity is slightly more significant in Indian monsoon record. That's because I think I probably don't have enough time to explain why East Asian monsoon has less glacial interglacial cycle, but Indian monsoon do have some interglacial glacial cycles there inside of the Indian monsoon. So in our East Asian monsoon record, it's just a pure precession signal, but Indian monsoon has some 100,000 year cycle there. So the difference is that we recently understood what happened. In East Asian monsoon, there is glacial, interglacial sea level components there. So that glacial, interglacial component canceled the influence from glacial, interglacial impact. But Indian monsoon doesn't. This is because the continental shelf is very extend really long distance during the glacial time because the sea level was low. Therefore, the source is far away. It could be like 1,000 kilometers away, the marine source for the East Asian monsoon. But the Indian side, they're totally different. Therefore, this effect canceled the interglacial glacial cycle in East Asian monsoon delta weighting record, because the source, the distance affect the delta weighting. But we did see this delta weighting difference in terms of the, for example, the glacial interglacial, this amplitude in Indian monsoon is like 8 per mil, but in East Asia it's only 4 per mil. So other 4 per mil is just because canceled, right? That's why we didn't see 100,000 years cycle. This is our story.
Thank you for the talk. I just got one question. So we've used a lot of delta O18 oxygen isotopes and also carbon isotope, of course. I just wonder if there's any chance we could you could talk about any use of calcium isotopes in speleothems and what they could tell us, if they can tell anything.
You mean carbon isotope?
Calcium isotope? Calcium?
Oh, calcium.
Yeah, do they tell anything?
Well, calcium, this, I think this is quite, I think it's, I saw a few papers there, right? And it's not that exciting to me, probably. Otherwise, I will do that, because we have the capacity. I mean, it's not a problem. Technically, it's not a problem. Just, it's not, to me, to be frankly, to my age, what you can do is limited. But you should concentrate on something you thought is more important. But calcium, the isotope, I'm not quite sure what direction they're going to go. What can it tell us? But probably could tell some detailed stuff, which could be maybe local stuff or whatever, but cannot really give you some information like delta weighting. Delta weighting, although it's a very older, like a proxy, it's still most important proxy because the nature of the isotope fractionation, it reflects larger scale circulations. So that's my view. Might not be right though. Right. You should think about it that there's a magnesium isotope. You could think about it. Silicon isotope. You can think about it. But recently, I think there are some GDGT stuff is really exciting. Probably, if you choose right, then you'll be able to more successful.
Okay. I think it's time for lunch. So thank you for coming to our Emiliani Lecture, and congratulate Dr. Hai Cheng.